Hello, everyone. Welcome to the KSEA Distinguished Guest Series. I am Young-Ki Kim, professor of physics at the University of Chicago and president of the Korean American Scientists and Engineers Association, KSEA. The theme of today's guest series is the second quantum revolution. We have three distinguished guests. So let me briefly introduce them. Jung-Sang Kim is a Shishano Family Distinguished Professor of Electrical and Computer Engineering and Physics at Duke University, and co-founder and Chief Technology Officer of IonQ Inc. His main area of current research is quantum sciences and technology, using trapped atomic ions and a range of photonics technologies in an effort to construct scalable quantum information processors and quantum communication networks. He's passionate about transitioning cutting-edge research into practical technology that has a commercial relevance. Na-Young Kim is Associate Professor in Electrical and Computer Engineering and Institute for Quantum Computing at the University of Waterloo. She runs a quantum innovation laboratory. Her primary focus is to build solid-state quantum devices and systems in both electrical and optical domains based on semiconductors, nanomaterials, and quantum materials by studying quantum electronics and optics, cavity quantum electrodynamics, and condensed matter physics. Her team also explores classical machine learning and quantum algorithms to deepen quantum devices and systems. Soon-Won Choi is Assistant Professor of Physics at MIT. As a theoretical physicist, his research is focused on quantum information science and its applications for studying exotic quantum many-body phenomena. He's interested in exploring dynamical phenomena and designing their novel applications for quantum information science. His research topic is extremely rich and often involves a wide variety of interdisciplinary approaches to study, from analytic theory and numerical computations to collaborations on experiment. Today's session will be facilitated by Professor Jung-Sang Kim. Now, please join me in welcoming Professors Jung-Sang Kim, Na-Young Kim, and Soon-Won Choi.
All right. Hello. Thank you, Professor Young-Ki Kim, for the introduction and actually organizing this wonderful opportunity for us to share some of our current thoughts and the progress in quantum information science and technology. I'm also extremely honored to be part of a panel with Professor Na-Young Kim and Professor Soon-Won Choi, some of our kind of rising stars, actually even already risen stars in the field, some Korean American and Korean origin researchers in the field. All right, so maybe I'd like to just start with some of my thoughts on where quantum information technology is. I'm sure many of you have heard about quantum information, quantum computing, quantum communication, quantum networks. It's actually starting to get discussed quite a bit, even in the very popular press. And you know, I myself studied physics at Seoul National University, started in the late 80s and early 90s, and pursued my degree in physics at Stanford University, working on some of the quantum optics topics in the past. Back in those days, the quantum physics was, you know, some of the most advanced devices that we work with, things like transistors, lasers. Now, they are basically definitely based on quantum principles, but my research really involved looking at some very exotic properties of quantum physics that we don't get to experience on a day-to-day basis. And you know, we hear about things like superposition states, which meaning a quantum state can occupy two different states at the same time. We think about entanglement. This means two particles are somehow correlated, and that correlation persists even if the interaction between the two particles are completely cut off. And some of these are, pretty exotic concepts. Concepts like entanglement that was introduced in the early 20th century. Even the most renowned scientists, physicists like Albert Einstein had a very, very difficult time accepting that as a phenomena. But what was really interesting in the late 80s, late last century, was the experimental physicists were getting extremely sophisticated with their tools that they can actually start to control quantum systems well enough to actually study these very weird and non-conventional phenomena at the atomic scale. So I certainly work with photons to look at some of these properties. And then, some of these controversial topics like entanglement has now been experimentally tested and proven to exist. And that was actually the experimental effort was really the topic of the Nobel Prize in Physics last year, right? So a lot of this work really happened as I was actually being trained as a scientist. But the other really interesting progress after that is there was a really interesting motivation to see if we can actually start to be much more purposeful about utilizing these exotic quantum phenomena. And that was basically the motivation was the real motivation was started in 1994 by a Bell Labs researcher back then, professor who's now a professor at MIT, Professor Peter Shor. He actually invented an algorithm, a quantum algorithm, that if you actually had a quantum computer, then you can factor numbers. Factor numbers means if you think about two prime numbers whose product is given to you and finding the two prime factors, that was believed to be an extremely difficult problem. And therefore, it was actually very practically widely used. So if you today go onto the internet and buy something from Amazon, and send your credit card information over, that information is encrypted using these public key cryptography. Professor Peter Shor's algorithm basically proved that security of that public key crypto system is not safe. And that actually spurred a lot of practical interest in this exotic quantum phenomena. And we actually had a pretty exciting about 30 years of ride where basic science, exotic quantum phenomena has actually been much more carefully exploited. And people have been putting a lot of engineering efforts to see if we can build systems that scale, that you can control them extremely well. Now, even to a point where commercially relevant applications are being sought after today. So in a sense, this was a tremendously exciting opportunity for a basic physicist like myself, who are trained in that field, to see the most novel concepts of physics that even the biggest minds in the community has been skeptical about, has not only been proven in the laboratory, but it's actually starting to be exploited and purposefully engineered to build systems that can potentially bring a lot of value to our activities. So this is indeed an exciting times. And of course, I personally caught that bug and got very, very passionate about taking this technology into potentially something of commercial relevance. And that activities actually has been some of the most exciting ride that I've had in my career. So with that background, I'd like to see if we can get the panelists to share some of their perspectives on this very exciting progress of the field. I would love to provide some questions that I've prepared, but also at the same time, if you have any questions along the way that you'd like to ask any of the panelists or myself, please enter those into the chat. And hopefully towards the end of the session, we'll leave out plenty of time for us to just have some discussions live with the panelists. With that, I'd like to turn the table over to Professor Soo-Won Choi. Soo-Won Choi.
Great, thank you so much for a very insightful comment, Jung-sang. Like, it was like, yeah, like to me, I'm a little younger in terms of academic age, and entanglement is something that I learned in my school years, rather than I trained myself as a scientist together with the development. So it was actually like, I can feel the type of excitement you must have had like throughout your career. And then, yeah, that's a beautiful story. Today I'd like to share a few slides and then present what I think about the second quantum revolution. So let me share my screen. So it's a very short presentation. The second quantum revolution. So what is the second quantum revolution? And maybe before asking this question, we need to answer the following question: what is the first quantum revolution? Second quantum revolution exists only when we had the first quantum revolution. So have we gone through the first quantum revolution already? And the answer is definitely yes. At the beginning of 20th century, a lot of new scientific development was made. And that's basically where the quantum physics has begun to start. Roughly speaking, at the beginning of the 20th century, maybe the first evidence is a Planck's law, where we started to realize that the light or photons exists in the quantized form. And then the next decade, we studied atomic models. Like we studied how electrons behaves inside atom and realized that their energy levels are also quantized. We have a certain energy levels. And later on, we started to realize how these photons and atoms interact with one another, and they learn about the interactions of these quantized objects. In the end, overall, the development of quantum physics is very tightly connected to a deeper understanding of atoms and light and molecules, and how they form larger systems like quantum materials. And usually, whenever there's a deeper understanding, we get new technological advance. And that's basically the first quantum revolution. For example, by understanding how electron behaves in material very well, we started to control electronic circuit and design electronic circuit. And eventually that has become the source of our existing information technology. At the same time, we started to understand how to manipulate light in a very coherent and engineered way. And that has become the source of the laser technology. And that's basically the basis behind our communication technology. These ideas, this set of ideas, is basically the idea that now we call the first quantum revolution. However, those set of technologies or idea, can be explained very clearly using quantum mechanics. However, they are not actively utilizing the unique features of quantum mechanics yet. And that was the context of the second revolution. From a theorist perspective, the second quantum revolution, the idea of utilizing the unique feature of quantum mechanics, has started in 1981. So this is a picture of the participants to the first conference on the physics of computation. And this was held at the Endicott House at MIT. And this was the combination of physicists and computer scientists basically talking about how to utilize existing advanced at that time, like computer technology, in order to advance our science. The keynote speaker to this conference was Richard Feynman. And actually, the Richard Feynman made a very interesting comment. Not only we should utilize advanced computing technology to advance science, maybe we should develop the new type of computer if you want to better understand the quantum mechanical systems. And the famous quote is that, if you want to build a simulation of nature, you'd better make it quantum mechanical. And this idea is now understood as the root of the idea of quantum simulation. And since then, this idea has been branched out to the different tasks. We can do quantum computations, as Professor Jang Kim explained nicely. Peter Shor pioneered algorithms to factorize products of prime numbers. We can develop new sensors, metrology, or develop new communication security, and so on. And we also developed new understanding behind what's going on these potential applications. And the key word is entanglement. This is a weird type of correlations that displayed by the quantum mechanical systems. What's really exciting, at least for me, like personally, is that this new development, entanglement, is teaching us about the basic science, this entanglement provides new perspectives to study, for example, quantum gravity, or quantum materials, condensed matter systems, or the basic sciences of statistical physics. And at the same time, we are currently developing new experiments and we're developing new technologies to realize this idea that we've been dreaming about. And this set of movement is what I call, what I understand as a second quantum revolution. In particular, the notion of entanglement is very interesting. So I'd like to spend a few minutes about explaining about this. So let's consider a system, and the system can be divided into two parts, A and B, and they are correlated. So we can think of, like, say, two coins, and you just flip the coin and then see head, tail, and head, tail. So you two outcomes. We talk about 2 degrees of freedom is correlated only when there's a randomness involved. For example, if you flip the 2 coins and say both coins are always tail, and it's hard to say it's correlated because there's nothing to be correlated. It's just always, tail, always head, nothing deterministic. Therefore, in the classical world, it is necessary that there's a certain level of, randomness. It's up and down and up and down. Only then we can talk about whether they are up together or like down together, and so on. So the randomness is a precondition for the correlations, but that's not true for the quantum mechanical system. In the quantum mechanical system, it is possible that the entire system does not involve any entropy or statistical randomness, but still the entropy of the subsystem could be non-zero, it could be larger. And what's happening is they share a bit of the information between those two, so that information is shared between those two in a way that you cannot tell this information only looking at the part of it. And that could be possible because, as we discussed about the examples, if you have 2 degrees of freedom, say 2 spin-1/2 particles, we can have a wave function that can be superposition in any of the 4 configurations. And if you consider superposition such as a Bell state, this pure state does not exhibit any entropy globally. However, we exhibit the correlations. And this idea of entanglement has found its applications to various practical applications, and also fundamental basic science, such as quantum simulation, which is what I'm going to explain a little further. So I'd like to emphasize that this quantum revolution is also bringing new insight to the basic science. And here I'd like to talk about one specific example, and that's the idea to combine quantum physics and statistical physics. Quantum physics is usually what we perceive as a physics at the atomic scale, single atom, single molecule, or maybe engineer a device at the extremely low temperature, like this chip made by Google. That's why we believe that where a quantum mechanical effect becomes relevant. On the other hand, in high school or in college, we learn about statistical physics. The statistical physics talks about collection of many, many particles, Avogadro numbers of particles, and they are interacting. And we cannot describe motion of individual particles. Rather, we talked about the statistical behavior, average energy, pressure, or temperature, and so on. And one of the most important governing principles on the left-hand side of quantum world is Schrödinger's equations. This is the differential equations describing how the state of the system changes over time. And this is a linear differential equation in time. The most important equations for the statistical physics is the second law of thermodynamics. It says basically a closed system has an entropy that never decreases. It can either stay the same or increases. But actually, there's an inconsistency between these two theory, columns of our modern theory, and that's the behavior about the time reversal. The Schrödinger's equations, in principle, everything is time reversible. This equation of motion is linear in time. That means if I change the sign of the right-hand side, in principle, we can undo the time evolution and go backwards in time, just like what we see in the movie Tenet. However, that's not the case in the second law of thermodynamics. Entropy is increasing over time, and due to this inequality, we cannot change the sign of the time. So we always move forward. Therefore, there's a certain arrow of time, and time is irreversible. And in fact, this discrepancy between quantum physics and statistical physics leads to actually contradictory predictions, and that's what I'm going to illustrate. Consider for now, our entire universe is made out of 2 types of particles, like hot particles, like high energy particles on the left, and low energy particles on the right blue. And then this is perfectly isolated from the rest of the universe, and consider quantum mechanical time evolution. You wait for a long time and let's study what happens. And our everyday intuition says these particles will mix one another, and then it'll spread over the whole systems somehow randomly. Therefore, the average energy will be uniformly spread over the system. According to quantum mechanics, this should be governed by the Schrödinger's equations. And then we need to ask questions. What is the entropy change of the system? If the entropy does not change, it's contradictory because the state on the right seems to have a more entropy according to statistical mechanics. So if the entropy does not change, our statistical mechanics is incorrect. If the entropy does increase, it seems like our Schrödinger's equation is wrong. So this leads to the incompatible predictions of the STEM math and physics. There's a tension between the two theory, and this is when the physicists become excited. Let's try to understand what's going on. And turns out quantum entanglement provides a solution to this paradox. And the answer is this. If you consider this system like mixed system and look at the whole system and divide into the two parts, some subsystem A and the rest of the system that I'm going to call B, turns out globally, the entropy does not change. However, if you look at the subsystem becomes entangled or correlated with the rest of the system due to quantum entanglement, leading to non-trivial entropy associated with this. Therefore, if you ask, what is the entropy change of the system? My answer is, the entropy of the global system does not change. Therefore, quantum mechanics is still true. However, the entropy of the subsystem still increases because the subsystem becomes correlated with the rest of the system due to quantum entanglement. Therefore, both quantum mechanics and the statistical physics are correct in these descriptions. So I talked about the specific examples of how quantum entanglement, or more generally, the idea from the quantum information science, allowed us to have a deepen our understanding about the basic science. I'm looking forward to the more of those kinds. And with that, let me finish my, my comments about this field. Thank you so much.
All right. Thank you so much, Professor Che. That was a very insightful example of potential conflicts and inconsistencies that resolves thanks to quantum mechanics. I would like to then turn it over to Professor Na-Young Kim to hear her perspective for a comment.
Great. Thank you very much. I'll also share my screen. And thanks for this wonderful opportunities. And this is a great chance to have conversations with us. And first of all, thank you, Professor Young-Ki Kim, for organizing this beautiful hour with the great panels and audience to have a conversations about the second quantum revolution. We had a great introduction by Professor Choi, and I'd like to give you some thoughts. And we all are immersed in various types and forms of information. And we contemplate a little bit, then we reach a thought that we on Earth will connect and communicate with nature, family of friends, and natural and engineered objects by giving information and receiving information. In this particular hour, we are here to talk about how to handle this information whose governing principle is based on quantum physics, which we already learned. It offers full of surprises and wonder against our intuition. We already learned the specific examples, since it is fundamentally different from our macroscopic world we experience every day. This peculiar aspect has been fascinating to me, although it is the big challenge to overcome our intuition. So, rooted from this quantum physics, we already learned that the eccentric phenomena of quantitation, entanglement, perfect correlations, wave particle duality, etc. At large, there are two pillars to drive the research activities of quantum information processing. I'm also a firm believer that the comprehensive knowledge in science leads to innovative technology we already learned. And advanced engineering and technology also enable us to explore profound scientific phenomena, such as the conflict between the quantum mechanics and the statistical physics we already learned to discover the beautiful underlying principles. Some of the key words are enlisted here in each pillar to constantly nudge me to think over what is the fundamental science concepts and what kind of technology we want to build. And I'm actually an experimental condensed matter physicist and engineer. I like to show my journey of the quantum research, and personal quantum revolution 1.0 is the era I built up strong foundation to learn about the quantum physics and acquire experimental techniques, mathematical framework, theoretical explanations, and to demonstrate quantum electronic and optical devices. And in fact, during this journey, I am indebted to many people and professors and mentors who influenced me greatly in science and life. And one day during my undergraduate, one of my friends actually brought the article, Quantum Computers in Physics Today. At that time, we consider it as a scientific fantasy. And I joined the Professor Yamamoto's group, and which is the group we built the quantum computer. It's a big dream. At that time, it is actually very skeptical. We call that the quantum computer is a millennia project because we are like 2000. And also it's like putting the elephant in a fridge. So that's kind of the skepticism. However, our groups are always excited, and because we dream the fundamental hard problems, which actually leads to the new technologies and amazing supports from the government fundings from Japan and the US. And we are able to see how this accumulate the knowledge in quantums and also device. And then furthermore, we see this commercial the companies and so on. And after 14 years in academia, I have a short excursion to the corporate in order to experience the real mundane industry life. But I admit that there is a different mindsets and organization structures and skills at Apple, and then it is truly invaluable. However, my yearning for the new knowledge and novel physics in quantum science and technologies leads me to join the Institute for Quantum Computing at the University of Waterloo in 2016, where we actually established a quantum ecosystem of academia, industry, and government to form so-called the Waterloo's Quantum Valley for more than 10 years. Now we celebrated 2 decades of the institution, and thanks to the strong support from the institution and government, now I'm actually in the Quantum Revolution 2.0, pursuing the research projects in the domains of quantum electronics and photonics, to name a few. We are investigating some of the materials, and also we are utilizing the semiconductor-based quantum simulators to the real-world problems. And recently, we are also working on Ripper exciton-based sensors and technologies. And during the last 25 years, I've witnessed the advancement of enabling technologies, which brings the even commercially available quantum computers to life. And I'd like to have some moments to appreciate this tremendous expertise and advancements by developers, scientists, and engineers. First is the cooling technology, which is actually leads to remarkable progress in superconducting and spin-based quantum computing platform. When I started, the Dilbridge is wet. What I mean by that is we have to utilize the expensive helium-3 system. And then the base plate we call is the area we have to put in the samples. It is about 3 centimeters. So it really requires a dexterous skills to put things inside. But about decades later, we are now the dry dilution refrigerator, which actually brings this base plates like 10 times large, so that you can imagine all of this beautiful experiments in Google, and then IBM actually puts the large still fridge. And last year, even IBM Q announced to build the most largest quantum computers, where they're going to put this thousands of the qubits. As you see that this base plate is about meters, so that this gentleman is working on installing the big computer. So we really appreciate the cooling technology advancement. Next, I also appreciate the nanofabrications and characterization technologies, which actually impacted all of the platforms in this era, and utilizing the laser and nanolithographies, we are able to design and fabricate the features like kind of tens of nanometers up to microns. Even recently, we can also do three-dimensional systems. We also achieved the atomic level of resolution in technology to grow the materials and characterizations. And recently, we also adopted the robotic arms to characterize or the proving of the systems, which gives a lot of flexibilities. And next, I also appreciate this detection schemes and control technologies. When I started to detect a single photon, we all based on these avalanche single photon detectors. And then the electronics to control the circuit is a NIM module. It's a kind of microwave, the kind of old technologies. And now we are using the superconducting material based on the single photon detectors, which allows us to have a massive parallel detections. And now you see that the 16 channels or 32 channels and so on. And furthermore, we have advanced the electronics, which has a compact for time taggings and so on. So this actually helps a lot of kind of the compact form factors of the quantum technologies. And the electronics is the same thing, because I start with this analog, the lock-in amplifiers and oscilloscopes, and then the digital and analog converters and so on. Now we are able to even arbitrarily generate the different forms, and then even the terahertz technology helps us to bring up the next generation, and field programmable gate arrays allows to have a handling the massive arrays of the qubits and control. And now this kind of system can even operate it by the iPad. So this is amazing technology, also helps us that. So at the end, at the heart of my heart is always on nature's, and the beauty and the wonder is the fascinating me. And as a physicist, the way to look at this, the beauty of the natural phenomena is through the different lenses, so-called the conventional, and they synthesize the materials, and also we can describe this phenomena as a beautiful physics or the mathematical way. And up to this understanding, and now we are designing of the devices and applications. I'd like to end a few words so that I'm continue to dream and perceive the ideas. And there are a lot of hurdles and challenges, but we actually stick to the perseverance to overcome. But one thing I learned that in order to have this amazing interdisciplinary technologies, in fact, we have to have the wonderful colleagues and competitors, so that this is the human things. So I'm very looking forward to the further conversations with you. Thank you.
All right. Thank you, for Professor Nayeon Kim. As I said, I've actually decided to, we've thought about some of the topics that we wanted to discuss, but please, if you have any questions you would like to ask the panelists, please feel free to enter those into the chat, and then I'll probably, hopefully towards the end, we'll have some time to go over these questions as well. So I'd like to start with maybe a little bit of a technology question, maybe for Professor Sung-won Choi. You're interested in the second wave of quantum technology. What do you think is the secret sauce, the underlying secret sauce that makes the second wave of quantum technology so special and so different from anything we have experienced in the past?
Yeah, thank you so much. I've been thinking about this question a bit. Okay, why? I cannot speak for the community, but I can speak about myself. Okay, why am I excited about this quantum science? And maybe I would like to talk about two aspects. The one aspect is, as a scientist and a physicist, I'm very excited about exploring new regimes, especially the regimes where the theoretical development and experimental advances go together. So in the field of physics, there are different subjects where the theoretical description is so specialized or experimental technique is so advanced, and they start to depart from one another. The theorists do their own thing, and experimentalists do their own thing. without not much of communication. Of course, they try hard to communicate each other. Sometimes it's difficult, but nevertheless, they try. But in this field of quantum information science, it's a young field where rapid experimental progress is being made. But in parallel, there's also rapid theoretical development that goes together, and they go hand in hand and then have a vibrant conversations. And that's one of the very exciting things that I find as a scientist. But more looking forward to the future, the second ingredient that I really believe that makes me excited about this field is this potential beyond imagination. So it's very ironic because I have to be very honest. Like once we build a quantum computer, what would you like to do? Well, maybe I would like to, hack the Amazon website by, breaking this public key crypto system. Maybe that's one thing, but that's not the only thing. There could be many other things, but really what makes me excited is not knowing what to do. It's a new toy, like it's a entire new things. And then I know that this could be used for some task that I couldn't even thought about existing. So for example, let's suppose we rewind our time, maybe 100 years ago, maybe 200 years ago, like 100 years ago is maybe good enough. When we started to build a computer, okay? And then maybe people thought about, okay, if you have a computer, maybe we can do some arithmetic calculation more efficiently. We don't have to do tedious calculation by ourselves, but maybe we can use these machines to do the computations, right? Maybe that's what I've been thinking. But let's look what we have now. I don't think, back in the past, 100 years ago, people will argue, hey, we need to build a computer because once we build a computer, you know what? We can build something that's called the smartphones. There's the app stores and the games. I don't think people could have imagined this at all. It is kind of many steps that eventually led to this tremendous amount of development. The same story is something that I'm expecting. For now we talk about building quantum computer, but who knows what? And this, like the sequence of discovery that's yet to be made is something that makes me excited. Maybe I spoke too much, so maybe other words to say too.
All right, no, thank you. That was a very exciting. We could feel the energy and excitement. Actually, the next question may be just following up on your comments. You did mention that, of course, when we started out many decades ago, we wouldn't imagine we would have smartphones, and actually having a video conference like this has been a dream for a very long time. I grew up people in science fiction movies having video conference, and that has just became the norm. We currently have 158 people, 159 people, all talking to each other over video. This is amazing progress, but it took a long time. It did take a long time, as you said. When some of the early computers were built, we didn't actually imagine these to be real. So I'd like to see if I can challenge the two panelists with some speculation that I'd like to see if you can make. Could each of you help predict some of the impacts on our everyday lives that these quantum technologies, the second wave of quantum technologies or quantum revolution, can bring, that will really change the way we think about things? Maybe we start with Professor Na-Young Kim.
Great, thank you. It is exciting questions and see because we have to dream, and some kind of mundane way to tell is that we believe that this quantum computers or technology will help us to have some hard problem to solve, like kind of complexity problems. For example, even we are talking about the health sector, how we can find the viruses. We went through this COVID era. So whether this quantum computers can help us to find the right virus or the right the drug deliveries and so on, then that will help us to have, whether all the people can perceive that's coming from the quantum computer, that's a different story. But then we are also looking into that aspect. And another one we can also think is that how quantum computers can impact this financial sectors or the industries. They could require some of the optimization problems to improve the procedures or the techniques. And then that is another error. And again, whether that's a direct or indirect experience by the everyday or all the peoples, but in fact that brings us the different like the life scale styles, I would imagine.
All right, Professor Chen.
Yeah, I think it's hard to predict the future, but if I can guess, I believe we'll change our expectation about what's possible and what's not possible in terms of technology. And also it'll change our perception of how to look at stuff and technology. So this is a bit abstract, so let me give some examples, okay? So we are talking about superposition principle, measurement, decoherence, entanglement. All sounds very abstract and exotic, okay? What's more kind of intuitive is okay, energy. You know, we have a lot of energy, and you know, we need to buy energy, we need to sell energy, we can change energy from electricity energy to some other form of the heat energy. Way more intuitive, right? So, but is it really true? Is there anyone who actually, you know, touched the energy, or is it anyone who actually, you know, bought energy, you know, and then put it in your pocket? No, like the notion of energy is very abstract concept, and it's very exotic concept, in fact. Nevertheless, because we are using the term energy in everyday life, energy is a commodity, it is a common resource, and it's a, you know, it's a commodity, and we actually need to buy them and we need to use them. I think the same thing will happen about the quantum mechanical, you know, concepts. Oh, I need more entangled pairs. I need the more quantum communication channels, you know. This sounds so exotic at this moment, because it's not available in our everyday life. But at some point, the quantum internet will play the important role in order to establish secure communication channels. And then people will start thinking about, hey, this quantum entanglement, my quantum entanglement channel is not so good because it's so noisy. I want to move on to a different company because, you know, they provide a better, more pure quantum entanglement, you know, and so on and so on. That also will change the way we perceive the communication technology. You know, oh, internet is so slow, therefore, you know, rather than doing this communication, let's do email. Like that kind of concept will change. Oh, you know, let's not use this protocol, but to maybe, I don't know, yet to be discovered protocol using quantum entanglement. So those kind of perceptions of what's possible and what's available, and the way people will perceive the quantum mechanics and their connection to technology will change. That's what I'm relatively confident about.
Great, thank you. I'm going to turn the question to Professor Na-Young Kim. You mentioned about you walked us through your career trajectory in quantum. If you can point to kind of one most exciting period in your career to date, when you felt like what you did was just so impactful that you got really excited that you contributed to a major progress in the field, what would that be?
For me, I think it's maybe I'll answer that in kind of change my perspectives about quantum computers. As I said, we started with the pessimistic aspects of the quantum computers and whether we are able to build. But after this, the Google announced that we're going to build the quantum computer. Actually, that announcement actually changed my thoughts, because at first I kind of, who wants to buy the quantum computer? It's so gigantic, so costly. But then the Google jumped in, then probably there's a reason they jumped in. And then suppose even like big governments or the big companies they could buy, then it is there's still markets for them to consider as a kind of the future. And furthermore, this cloud service also changed my mind too, because I thought that I have to own the quantum computers, but not anymore, because the quantum computers can be built in somewhere there, but I can access through the cloud service. That actually changed the whole perspective. So we don't have to have always a compact quantum computers or the like kind of computer in front of me, but there's a powerful computer, just like supercomputers somewhere out there, but we could pay to have that access. We don't have to utilize all the time, but specific problems that we want to solve, we know that that's done by the quantum computer well, then we could actually go and then use that. So that two services actually changed my perspectives.
Okay, that's good. All right, maybe I'll ask the last question, then we'll go there. We are getting a lot of questions on the chat, so we'll try to get to those. Maybe one quick question to both of you would be, you know, it looks like quantum is all a very exciting area. We're all, it looks like we're already pursuing our careers in this field, but at the same time, it is so new that there seems to be a lot of risk and uncertainty about the future. And just jumping into it as a career, do you have any advice for some of our young students and young scientists who is willing to jump into this field about how to think about their future in their careers? Maybe Professor Kim, will go first.
I think I am also by training physicist, and then again at the start, the majorities of the scientists who works on quantum computer is physicist, but now it's the engineering phase, so that it is interdisciplinary, and we need a lot of different the background people like computer scientists, electrical engineers, mechanical engineers, and then the even the other types of the engineers, so that they but then those people not necessarily understand all this, the profound, the quantum physics. And now we can also approach this, the quantum in terms of circuits. Then people are able to have a lower the barrier to enter this field, so that I don't think as you have to take this quantum mechanics 101, it's not anymore the start, so that there's a lot of tutorials. You can even build the quantum programmings using the free softwares and so on. So that's but then what I like to emphasize, not only technical intelligence, but then you have to have a passion and then interest. Then that actually overcomes any barriers. So that's my thought.
Thank you. Professor Choi, do you have anything you wanted to add to that?
Actually, I absolutely agree with Professor Nayan Kim. Like, essentially, the landscape of education system has been changed dramatically. If you just search, say, YouTube about quantum science and quantum information and quantum computing, there are like enormous amount of resources and targeted for the different levels of audience. So no matter where you're coming from, whether you are already advanced or whether you're a beginner, like maybe fresh out of high school, just try to learn from those resources, and they are very good resources. And also I would like to emphasize is that your interest matters the most, as your and also your passion. So I'd like to second that.
Okay, great. All right, so I'm going to see if I can put a big challenge onto this panel, and including myself. Now, there are lots and lots of questions. Instead of trying to select them, I'm going to try to run through every one of them until we catch up. So what that means is I'm going to designate, we can either volunteer or I'm going to designate the question to one of the panelists, and then we're going to give them 30 seconds to answer it. Okay, so we can run through a bunch of questions, no longer than 30 seconds. First question is from Jin Chung. Hi there, can you say something about your particular experiments and how you handle measurements and decoherence of the quantum computer you're experimenting on? Can you also shed some light on how you approach error correction? I think this
maybe
is
for the experimentalist, yeah.
Yeah, it is for experimentalists. All right, Professor Nayan Kim, do you want to take it? If not, I'll take it.
Yes.
All right. So in our system, we use individual atoms, and these atoms have internal states, and that's what we use as the qubit. And then when you do a measurement, we actually wanted to collapse the coherence into one of the two states, and we can illuminate the atom with some very specifically tailored light, so that if it's in one state, it will actually continue to scatter photons, so the atom glows, and in the other, it does not. And that is how we actually determine the state of the readout. We basically shine a laser beam and see if the atom glows. All right, out of time. Next question from Victor Kim. Is it possible to calculate 1 + 1 using quantum computing? If so, please show the code. I'll take this one too. Yeah, go ahead, please.
Okay, it is possible. It requires a few gates, namely Toffoli gate and control NOT gate, and 1 + 1 = 2 can be implemented in the existing quantum hardware almost from any platform.
Great. Thank you. Next question is from Kenneth Park. Could you explain the difference or similarities between quantum computing and quantum communications? All right, I'll take that one. So yeah, just like we have computers and communications, computing is actually processing information and communicating is actually sharing information between the two. Actually, for quantum communications, you actually have to be able to use quantum bits, entangled bits, and so on. So you can actually start to distribute quantum resources between two different quantum objects. And just like we had a communication network for the first 100 years was telephones, because at the endpoints were people talking to people, it's starting to shift to machines talking to machines, and that's where digital internet is the key. For quantum communications to prosper, we'll need quantum objects talking to quantum objects, whether quantum computers or quantum devices or quantum sensors. And I think that will be a very, very exciting future where a lot of very interesting things can happen. Next question. Hello, do you all have any estimation as to when quantum computing technology will be mature enough to be commercialized? In the next 10, 20 years, more or less?
Maybe I can take this one. So my answer is that the quantum computer has been commercialized already. The relevant question is who's the users? I'm one of the users. Current existing quantum devices is useful in order to test the capability of existing quantum devices or test the performance of a quantum error correcting code. So we are just experimenting, stuff to improve further. At the same time, recent analog quantum devices started to produce the data where otherwise you cannot, obtain using classical computers. So in some sense, it's already providing the unique set of data.
Okay, thank you. The next question is a little bit of a philosophical one. Some people say that it may be possible that the current world as we see now is not real, but it is a simulation. As quantum physicist, what do you think about the likelihood of simulation universe idea? Professor Young-Ki Kim, you're more than welcome to jump in. Anybody?
I can say a few words.
Yeah.
So, simulation has a particular implication. But let me talk about the computation. So, is our universe like computation, or then we need to define what the computation is. In my view, the quantum computation is broadly defined. We have an input, and there's an output, and there's a certain rules dictating how input transforms to output. And this rule is called the law of nature. Therefore, in the world, I believe that this entire universe is gigantic computations. Constantly at every time we have input for the output of the future, and then we are doing the computation. A more interesting question is whether this computation can be modeled using the classical computer, the theoretical model of the computation, so-called the Turing machines, or this is beyond our model of computation that necessitates our modification to the theory of computations. So people believe that quantum computer is beyond the capability of the existing computing machine called the Turing machines, and that's one of the things that's also exciting about connecting the basic physics and basically the philosophy of science to this quantum industry.
Thank you. Next one, what would be the most exciting application you envision for quantum computers in the near future? I would be interested to hear the perspective of esteemed scholars as a graduate student newly embarking on a career in superconducting qubits. Professor Nayan Kim, any answer to that? Tough one. You're muted, or you can't hear you.
Most exciting application is depending on your perspective, right? So maybe perhaps we can solve the quantum game, then that would be also exciting applications for the graduate students.
All right, thank you. I'd love to hear your opinion on how modern digital computers compare to what Richard Feynman originally described. For example, analog quantum computer. Yeah, go ahead.
If I jump in, like maybe Richard Feynman had just conceiving the idea that there's some kind of quantum machine can solve the hard problems. And now the modern quantum computer might not be even like kind of imagine it, but what he actually thinks is that the universal quantum computer can solve all complex quantum problems. Our current modern digital quantum computers are not yet there. In other words, it's not the full tolerant level. In other words, also that we haven't actually implemented error correcting the schemes on this regime, and that's what we are heading for. So hopefully we are reaching that regime and which our Feynman conceives.
Okay. Next one. Because of time, we may have to cut it off. Unfortunately, we may not be able to get to all the questions. The last one is the advantages of quantum computing come from superposition and entanglement, which is kind of superposition. But superposition is a universal property of not only quantum, but classical waves. What is the fundamental difference between quantum wave function and classical wave that distinguishes one from the other? Any thoughts? I have some thought. So superposition is definitely it is true in any linear systems. I think one really important difference is quantum states are still based on very distinct states that you can actually identify and differentiate. So it is actually, while you have a superposition of different states, you actually have the ability to eventually measure one or the other states, and that actually is critical in actually reading out information. So I think, and I believe that will be the main difference. All right, with that, I'm sorry I couldn't get to many more insightful questions. I really appreciate all the participants for sending us questions that we can discuss over. And I'm going to turn this over back to Professor Young-Ki Kim, who has a very exciting last event for the meeting.
That's right. Thank you. Wow. It was a fantastic and very inspiring and exciting session. And everyone, please join me in thanking our speakers, panelists, the professors, Jung-Sang Kim, Na-Young Kim, and Sunan Che for today's very inspiring presentations and conversations. Also, I'd like to thank you all for your outstanding, it's amazing engagement. They're full of very nice questions and it was very nice. Now it is the raffle time. So while our IT manager, Joseph Kim, prepares for raffle, I want to actually announce one KSEA Distinguished Guest Series that you might be interested in attending. 4 weeks from today, so there will be Wednesday, May 17th, 8:30 p.m. ET, like exact same as today. We'll have a session on ChatGPT. So I'll put the date and time and Zoom link in the chat box. So please mark your calendar. And of course, you'll receive announcement via email. Now I'll turn this to Joseph.